limited way that could be the case. I'm not convinced myself, but there's, but on average, the cold days are less cold. There's no question about it. Okay, so now let's get to something more interesting. What about floods? So I've been giving this talk for a while, so this is an old example now, but this was the South Carolina flood in 2015. I don't know if you remember. There was a hurricane offshore, which isn't actually what caused the flood. The flood was caused by rain. It was Hurricane Joaquin. Anyway, this was a house in South Carolina that was completely inundated, as was a large region. This is the situation. This is a satellite image from about that time that flooding was happening. Here was Hurricane Joaquin offshore. You see this big band here. There was a sort of a large organization, a large rotating circulation around this hurricane, and there was a wind blowing onshore and a big cold front here, and the moisture the hurricane got trapped as it was rotating with another disturbance, and it sort of stuck around here for a while, and the moisture was being steered onshore, and the moist stream of air just kept pointing at the same place, and as it hit the cold front, it was forced to rise, and the water vapor just rained out, and because it didn't move, the whole feature stayed stationary for some time. It just kept raining in the same place, very heavily, tropical rainfall, as the warm, moist air came up from the tropics, into the United States, and so you got these big floods in South Carolina. So the simplest way, so we are quite convinced, and all our models tell us, that heavy rainfall events like this will get heavier. And in fact, the observations, to the extent that they're good enough to see it, because there's a lot of noise, a lot of natural variability in the observations, but the observations show it happening too. And we're pretty confident that we know why this happens, and it's not entirely simple, but there's a simple way of getting the basic understanding of it. If you just imagine that somehow all the circulation features of the atmosphere don't change, like this hurricane is still there, and the jet that's blowing into the shore is still there with the same frequency in the future climate, that somehow the weather doesn't change, but all the air has more water vapor in it because it's warmer, just like we see is already happening, then that's just that much more water vapor that'll get squeezed out. Heavy rain events like this are very good at taking a lot of the water vapor that's in the atmosphere and dumping them out on land or on the ocean. And so if you just, even though it's not really true that the whole atmospheric circulation will stay exactly the same, it seems to be true enough. Basically, the effect of having more water vapor winds is a big enough effect that we get heavier rain events. And the amount of water vapor increase you get is about 6 or 7%. The basic physics, this is just very basic physics, it's called the Clausius-Clapeyron relation. It's just the thermodynamics of water vapor phase change, how it, when you get condensation, you can hold about 6 or 7% more water vapor for every degree centigrade of temperature increase. So that's a rough estimate for how much heavy rainfall events can change. The total amount of rainfall on the Earth, by the way, doesn't increase that fast, that much, because it's controlled actually by different things. It's controlled by the radiation budget of the Earth. So the overall rain on the planet is not going to increase this quickly. It's increasing, but not this much. But the extremes actually increase faster than the mean, because the extremes are very efficient at squeezing water vapor out. That's why they're extreme. Although there's a lot more detail than that, and a lot of my own research now is about heavy rainfall events like this and the physics of them and how the storm circulations actually may change. But we're pretty confident that just the water vapor effect is so big that that's why heavy rainfall events are getting heavier, and they are, and I'll show you a graph of that. This is actually just to show you some observations. We don't like to rely on models when we have observations to look at. This is for New York State. So this is a map from a report actually put out by the State Attorney General's office a couple of years ago. This is the observed change in very heavy precipitation. So actually, and I don't actually remember how they define very heavy precipitation. I think it's, I don't remember, but there's some measure of heavy rainfall events. It's increasing everywhere in the country except Alaska and Hawaii, and increasing most in the Northeast. This geographic pattern I don't think we understand so well, by the way, why it's increasing so much more in the Northeast. Some of this may not be climate change. Some of it may be natural variability. But the fact that it's increasing everywhere is suggestive that some of it is due to the warming. And this is the trend for the average number of, that's what this is. This is the increase in the percentage of rainfall for the year occurring in very heavy events, which I think means over 2 inches. And this is the annual average average number at a lot of New York weather stations, how many times per year you get at least 2 inches of rain in one shot. And it's hugely noisy. It goes up and down, but you can see an increase over time. And some of that is likely due to warming, even though obviously there's a large amount of natural variability and fluctuation in here that we can't explain from climate change. So that's just New York, to give a local example. What about droughts? So this is a picture of Lake Mead outside Las Vegas, the opposite of floods and droughts. Outside Las Vegas, a lot of people depend on this reservoir for water. This is a few years